In the last segment, we saw a very important application of DFS for directed graphs, that of finding strongly connected components in such graphs. And you will see later on in using algorithms that finding strongly connected components is a very important subroutine that you use for many, many algorithms on directed graphs. Now we will turn to undirected graphs again that we originally thought about, and we will show an application of DFS on undirected graphs. And this application is for finding what are called the biconnected components of an undirected or of a graph. So we say that a connected graph is biconnected if removing any one vertex leaves the graph connected still. This is a kind of a reliability property. If you think of a graph as a network, if you think of it as a network, and if you have an enemy who might be able to come in and take out one of the nodes in the graph, you would still like the property that the network is connected. So a biconnected graph is a little bit more reliable than just a connected graph. So everybody can still talk to everybody else, even if somebody took out one of the nodes in the graph. So it's a desirable property. Now, of course, not all graphs are biconnected. When a graph is not biconnected, we can separate it into what are called biconnected components, sort of like strongly connected components, but a little bit different as well. So a biconnected component is a maximal subset of the graph that is biconnected. So if you look at this graph here on the left, you find that the purple vertices, A, B, C, D, E, form one biconnected component. You can check for yourself that removing any one of these vertices will still leave the other four connected. The sort of orange vertices, C and F, form one biconnected component. And the green triangle FGH forms another biconnected component. So there are three biconnected components in the graph here. Notice one thing that's different from a strongly connected component. A strongly connected component components, it's an equivalence relation on the vertices. So each vertex can belong to only one strongly connected component. It'll turn out that biconnected components is an equivalence relation on the edges. So each edge can belong to only one biconnected component, but vertices can belong to multiple biconnected components, as shown in this picture. The vertex C and the vertex F each belong to two different biconnected components. So why is biconnectedness an equivalence relation on the edges? We will say that two edges UV and RS are equivalent if they're in the same biconnected component. And it turns out that another way of saying this is that two edges are in the same component if and only if there's a simple cycle connecting them. So a cycle that does not repeat any vertex except for the first and the last, that contains both these edges. Every edge is in relation with itself. We define the relation so that UV is always in relation with UV. Now you can see this relation is reflexive, basically because I've forced it to be so. I've said that every edge is always in relation with itself. It's also symmetric just by the nature of the definition. What is the definition? Two edges UV and RS are in relation if there's a cycle that contains both of them. So if UV is in relation with RS, there is a cycle like that, and that cycle also shows that RS is in relation with UV. Transitivity is a slightly trickier part. Supposing we have three edges, and we know that E1, which is UV, is in relation with E2, which is RS, which is in relation with E3, which is XY. So then you can work it out, but let me just draw a picture here. So here is E1, here is E2, and here is E3. So that means because E1 is in relation with E2, there's a simple cycle that contains both E1 and E2. So that cycle might look like something like this. And then there's another simple cycle that contains E2 and E3. That cycle might look something like this. And therefore, you can kind of see a cycle that contains both E1 and E3 right here in this picture. Of course, the cycle that you can get by following the path that's described in the proof may not be simple because you might repeat vertices there might be shared vertices between the two simple cycles we have here. But you can take a cycle that's not simple and get rid of duplications, cut out short loops in the middle and make the cycle a simple cycle that contains E1 and E3. So this shows that E1 is in relation with E3. So this is an equivalence relation on the edges of the graph, and that allows you to partition the graph into its biconnected components. All the edges that are in one equivalence class lie in one biconnected component. So how do we find biconnected components? Before we do so, let's talk about one more concept, which is an articulation point. A vertex is called an articulation point if its removal disconnects the graph into more than one component. So in this graph, again, the same example graph, vertex C is an articulation point because upon removing C, the top 4 vertices get disconnected from the bottom 3. So C is an articulation point. So now if you look at the DFS tree, suppose you did DFS on this graph starting somewhere, in this case starting at vertex B. You look at the DFS tree and look at what happens to C. So what you see is that this vertex C, which is an articulation point, has one child, in this case child F, such that if you look at the entire subtree hanging below F, that's subtree, there's no edge coming from that subtree and going above C. There's no edge from this entire subtree, a back edge that goes above C. Recall that in a DFS of an undirected graph, there are only 2 kinds of edges, tree edges and back edges. So the only way that this subtree hanging below C, rooted at node F, can connect to the rest of the graph, outside of connecting through C, is if there were a back edge going all the way from this tree to somewhere above. If there is no such back edge, then we know that upon removal of C, this subtree will get separated from the rest of the graph. So when this happens, we've found an articulation point. Now the condition is this is the general rule for finding articulation points for points in the middle of the DFS tree. Basically, a vertex like C is an articulation point if it has a child like F, such that the entire subtree rooted at F does not have a back edge going above C. So that's the rule for finding articulation points in the middle of the DFS tree. For the root, the condition is a little bit different. If B is the root node, and this is not the case in this picture, but in another picture, B is the root node and it has 2 children, we know that there is no edge from the left subtree to the right subtree, because that would not be a back edge, that would be a cross edge, which is not allowed in the DFS, which does not arise in the DFS of an undirected graph. So if the root has more than one child, it's automatically an articulation point. But for any non-root vertex like C, the condition for it being an articulation point is what we said earlier. So let's take these ideas and translate them into an algorithm. So since DFS on undirected graphs produces only tree and back edges, the subtree Ti rooted at child Vi of V will be disconnected by removing V when there are no vertices in T with back edges that reach above V. So what we will do is that we will give to each vertex something called its DFS number. This is not any different from the number which we called the start of the vertex V in the previous segment. A couple of segments ago, when we described DFS first, we said we defined a time or a counter or something like that, which steps every time we either discover a new vertex or finish with a vertex. And we defined the start of vertex V and the finish of vertex V. So the DFS number really corresponds to the start time of vertex V. So the root gets the number 1 because it starts in the beginning, and the first vertex discovered from the root gets the number 2, and so on. And note that ancestors always have smaller DFS numbers than descendants, because you always discover the ancestor first before discovering the descendant. And then we will, for each vertex V and each subtree rooted, Ti rooted at a child of V, let me show you a picture here. Here's the vertex V, and it has a child, and let's call it Vi. And under Vi is the entire tree of things. We don't know what it is, but it's some big tree Ti. So for each vertex V and each subtree Ti rooted at a child Vi, we compute the smallest DFS number reachable by a back edge. So maybe there's some vertex here that has a back edge all the way to here. And that would be a pretty small number. The higher you go up in the tree, the smaller the number. So we want to see how high do back edges reach from Ti. And we compute the smallest DFS number reachable by a back edge from any vertex in Ti. And we will call this the low number, the low of Vi. And the point that we made earlier, slightly more precisely, is that if low of vi is at least the DFS number of v, meaning that no back edge went above v, then v is an articulation point. And I hope that that is clear from the properties of the DFS algorithm that you now know. You can see the algorithm graying out the vertices and assigning DFS numbers. Let me run through it. This part is just assigning DFS numbers. We don't show the low numbers until we've fully computed it. And we only will know the low number of a vertex when we finish with it, because we'll be accumulating low numbers from below. So what I want to point out is how the low number computation is done. That's the key part. We're doing DFS starting at vertex u, let's say, a modified DFS here. For each v that has a color white, basically this v is going to end up being a child of u now. So for each v that has a color white, we're going to do DFS of v. This means that in the DFS tree, v is going to be a child of u. And what we do is articulation visit recursively. We increase the number of children of u. And finally, after we finish with v, we've computed the low number of v. If the low number of v happens to be less than the low number of u, so the picture is like this. Here is vertex u. While doing DFS of u, we discovered a new white vertex v. We did DFS of v. We found an edge going way up, a back edge, and so v got a pretty low number. So low number of v is very small. Meanwhile, u, so far, we haven't found any back edges that go that high. So if that happens, low of v is less than low of u, then we make low of u equal to low of v. Because remember, low of u is the smallest DFS number that can be reached by a back edge from the entire subtree that lies below u. So you can see that we need to assign low of v to low of u. So that's how we update low numbers. For each child of u that we visit, we update low numbers in this manner. And in the end, we'll have the low number of u. So you can see this algorithm continuing. So we're still assigning DFS numbers. But now that we've finished with vertex h, for example, we find that h had a back edge to the vertex whose DFS number was 3, that's f. And so the low number of h is actually 3. This means that the low number of h is smaller than the DFS number of its parent g, which is the parent g has a DFS number 4. 3 is smaller than 4. So g is not an articulation point because its child does not has a low number that's smaller. When we get to g, its low number is going to be also 3 because it has something underneath it that has a back edge to a vertex number 3. G's low number 3 is just equal to the DFS number of f. This means that f is an articulation point because there is no edge from the subtree rooted at g that reaches above f. So we found f is an articulation point, and in fact, all the vertices that we've discovered, which are black right now, can be taken off and put into a biconnected component by themselves. F, G, H forms a biconnected component, and we continue. We're back at C, and we explore the other child, A and E and D. And when we finish with D, we find that its low number is 1 because there's a back edge all the way to the root. So D's low number is 1. E inherits that low number. So E knows that its low number is also 1 because under the tree, under E is D, and there's a back edge from there to 1. So E has a low number of 1, and A has a low number of 1 as well. The low number of C is also 1, but we also noticed that C has a child whose low number is at least as much as the DFS number of C, and therefore C is also an articulation point. And finally, vertex B, it's a root, and it's not an articulation point because it has only one child.